Real-world applications and medians. Welcome, everyone. Before we dive into today's lesson, let's take a moment to reflect on what we have already covered. In our previous sessions, we focused on the theoretical foundations of geometry, specifically exploring the various criteria used to prove that two triangles are similar, namely, the angle-angle, side-side-side, and side-angle-side criteria. Today, however, we are going to shift our focus. We are moving from pure theory into practical application. I want to show you how these mathematical rules aren't just marks on a page, but powerful tools that allow us to measure things in the real world that are otherwise impossible to reach, such as the height of a massive tree or a tall building. Furthermore, we won't just stop at measuring heights. We will also investigate how the concept of similarity extends deeper into the properties of the triangles themselves, specifically looking at how it affects elements like their medians. So, let's get started by looking at how we can use shadows to measure the world around us. 1. Indirect measurement. On this slide, we introduce the concept of indirect measurement. Now, think about a time you wanted to measure something massive, like the height of a skyscraper or the distance across a wide river. You can't exactly climb to the top with a ruler or stretch a tape measure across a canyon, right? That is where indirect measurement comes in. It is a clever technique that allows us to calculate the height or distance of objects that are simply too tall or too far away to measure directly. So, how do we do this mathematically? As you might have guessed from our previous lessons, we achieve this primarily by using the AA, or angle-angle, similarity criterion. By finding two angles that are the same between a small object we can measure and a large object we cannot, we can create proportional relationships to find our answer. Now that we have covered the theoretical rules for triangle similarity, specifically the AA, SSS, and SAS criteria, let's move into how we actually use these tools in real life. The concept of shadow measurement. Now, before we jump into the calculations, we need to understand a fundamental physical assumption that makes this whole method work. When we talk about shadows, we are looking at how sunlight interacts with objects. On a large scale, when the sun shines on objects here on Earth, we consider the sun's rays to be parallel to one another. What does this actually mean for our geometry problem? It means that at any specific moment in time, the angle at which those sunlight rays hit the ground is exactly the same for every vertical object in the same area. Whether it's a tiny stick or a massive lamppost, the angle of the sun remains constant. This is the secret ingredient that allows us to claim that the angles in our two different triangles are equal, which, as we will see in the next slide, is the key to using the angle-angle similarity criterion. Real-world example. Finding the height of a lamppost. Now, let's put that theory into a practical scenario. Imagine you are standing outside and you want to find the height of a tall lamppost. However, you don't have a ladder or a long enough measuring tape to reach the top. All you have is your own height and a measuring tape to measure shadows on the ground. To solve this, let's identify the specific pieces of information we have to work with. First, we have the height of the person, which we will denote as h sub p next. We have the length of the person's shadow, which we'll call s sub p then. We look at the lamppost and note its shadow length, represented as s sub l finally. Our goal is to find the unknown height of the lamppost, which we will label as h sub l. Keep these variables in mind, because in the next slide, we are going to use them to set up our geometric proportion. Step-by-step process. First, we need to identify the triangles. I want you to visualize two separate right-angled triangles. The first triangle is formed by the vertical lamppost, the horizontal shadow it casts on the ground, and the diagonal ray of sunlight hitting the tip of the shadow. The second, smaller triangle is formed by you, the person, your own shadow, and that same ray of sunlight. Second, we must establish the right angles. Since we assume both the lamppost and the person are standing perfectly vertical to the ground, we know that both of these triangles contain a right angle, which is 90 degrees. Third, we need to establish a second angle. Remember what we discussed in the previous slide about the sun's rays? Because the sun is so far away, its rays are considered parallel. This means the angle of elevation, the angle where the sunlight hits the ground, is exactly the same for both your shadow and the lampost's shadow. Fourth, this allows us to apply the AA criterion. Since we have now identified two equal angles, the 90-degree angle and the angle of elevation, we can mathematically prove that the triangle formed by the lamppost is similar to the triangle formed by the person. Fifth, once we have established similarity, we can set up a proportion. Because these triangles are similar, their corresponding sides must be in the same ratio. This means the height of the lamppost divided by the height of the person is equal to the length of the lamppost's shadow divided by the length of the person's shadow. In mathematical terms, we write this as h sub L over h sub P equals S sub L over S sub P. Finally, the sixth step is to calculate the height. We just need to use some basic algebra to rearrange our formula to solve for the unknown value. By multiplying both sides by the height of the person and dividing by the person's shadow length, we get our final working formula. H sub L equals the quantity S sub L times H sub P, all divided by S sub P. Now that we have our data from the previous slide, let's walk through the step-by-step process of how we actually use this information to find the height of that lamppost. Once you plug your measured values into this formula, you'll have the height of the lamppost without ever having to climb it. 2. Similarity and medians. First, let's make sure we are clear on what a median actually is. If you take any triangle and draw a line segment from one of its vertices straight to the exact midpoint of the side directly opposite to it, that line segment is called a median. Now, here is the key property I want you to note down. When we are dealing with two triangles that are already known to be similar, a very special relationship exists between their medians. Specifically, the ratio of their corresponding medians is exactly equal to the ratio of their corresponding sides. In other words, the scale factor that relates the sides of the triangles also applies perfectly to their medians. We will spend the next few slides proving exactly why this is true using a step-by-step logical breakdown. Now that we have seen how similarity can help us measure things like the height of a lamppost using shadows, let's shift our focus from practical measurements to a more theoretical geometric property. We are now going to explore similarity and medians. Theoretical explanation. Now that we've seen how similarity works with shadows, let's move from practical applications to a more formal geometric proof. On this slide, we are looking at a very powerful property regarding medians. The core idea here is this. If we start with two large triangles that are similar, it's not just the main triangles themselves that share this relationship. The smaller triangles created by drawing medians inside them are also similar to one another. To prove this, let's walk through a step-by-step logical breakdown. First, we must establish our starting point, or our given condition. Let's assume that triangle ABC is similar to triangle PQR now. Because we have already established that these triangles are similar, we can immediately conclude two very important things. First, the corresponding angles must be equal. So, angle B is equal to angle Q second, the corresponding sides must be in the same proportion. This means that the ratio of side AB to side PQ is equal to the ratio of side BC to side QR, which is also equal to the ratio of side AC to side PR. Keep these equalities in mind, because in the next few slides, we are going to use them to introduce the medians and prove that the smaller triangles we've created follow this exact same proportional pattern. Introduce medians. Now that we have established the initial similarity between our two main triangles, let's introduce the medians to see how they behave. Suppose we draw a line segment, which we'll call CM, starting from vertex C and meeting the midpoint of side AB in triangle ABC similarly. In our second triangle, PQR, let's draw a median called RN, which connects vertex R to the midpoint of side PQ. We are going to use these specific segments to prove that the ratio of these medians remains consistent with the ratio of the sides we discussed in the previous slides. Analyze the midpoints. Now, let's take a closer look at what it actually means for these lines to be medians. Remember from our definition that a median connects a vertex to the midpoint of the opposite side. So, in our two triangles, we have point M acting as the midpoint of side AB, and point N acting as the midpoint of side PQ. Because these points are midpoints, they essentially split their respective sides into two equal parts. This means that the length of the segment BM is exactly equal to 1/2 of the length of the entire side, AB. Similarly, the length of segment QN is equal to 1/2 of the length of side PQ. We need to keep these specific relationships in mind, because in the next step, we are going to substitute these values into our original ratio to see how the sides relate to one another. Establish side proportionality. Now, let's connect what we just established about the midpoints back to our original similarity. From our initial condition in the previous slide, we know that the ratio of the sides of the large triangles is equal. Specifically, the ratio of side AB to side PQ is equal to the ratio of side BC to side QR. Now, remember from the last slide that M and N are midpoints, which means the full side lengths are actually twice the length of these smaller segments. So, if we substitute 2 times BM for AB and 2 times QN for PQ into our ratio, we get 2 times BM over 2 times QN equals BC over QR. As you can see, the 2 in the numerator and the 2 in the denominator cancel each other out perfectly. This leaves us with a very important result. The ratio of these smaller segments, BM over QN, is exactly the same as the ratio of the original sides, BC over QR. This is the crucial link we need to move forward and prove the similarity of the smaller triangles in the next step. Apply SAS Similarity. Now that we have identified our proportional sides and our shared angle from the previous slides, let's bring it all together to prove our similarity. Looking at triangle CMB and triangle RNQ, we can clearly see the criteria for similarity are met. First, as we established in the last slide, the ratio of side BM to QN is equal to the ratio of side BC to QR, which means we have proportional sides. Second, we already know from our initial similarity that angle B is equal to angle Q, which serves as our included angle. Because we have two pairs of proportional sides and the angle trapped between them is equal, we can officially conclude that triangle CMB is similar to triangle RNQ by the SAS Similarity Criterion. This is a crucial step because it sets us up for our final conclusion in the next slide, where we will show that this similarity extends to the lengths of the medians themselves. Final conclusion. Now, let's bring everything together to reach our final conclusion. Since we have just successfully proven that the smaller triangles, triangle CMB and triangle RNQ, are similar using the SAS criterion, we can apply the fundamental property of similar triangles. Their corresponding sides must be in proportion. This means that the ratio of the side CM to the side RN is exactly equal to the ratio of side BC to side QR. If you look closely at what this equation represents, you'll see the beauty of the proof. We have just demonstrated that the ratio of these two medians is equal to the ratio of the corresponding sides of our original, larger triangles. This confirms that the property of similarity extends perfectly from the main sides of the triangle to its medians. Key takeaways. First, let's revisit the concept of indirect measurement. As we saw with our lamppost example, we don't need to physically climb a tall object to measure it. By using the angle-angle similarity criterion, we can determine the height of inaccessible objects simply by comparing their shadows to the shadows of objects whose heights we already know. Second, it is crucial to remember the underlying assumption regarding parallel rays. In our shadow problems, the entire logic depends on the fact that the sun's rays are considered parallel. This is the specific detail that allows us to mathematically establish that the angle of elevation is identical for both the person and the lamppost, giving us that second necessary angle for our AA criterion. Third, we explored a very important property regarding medians. We proved that if you have two similar triangles, it isn't just the outer boundaries that maintain a consistent ratio. The ratio of any two corresponding medians, those lines connecting a vertex to the midpoint of the opposite side, is exactly equal to the ratio of their corresponding sides. Finally, we observed the concept of subtriangle similarity. We demonstrated that when a median is drawn, it actually divides the original similar triangles into smaller, new triangles. The beauty of this is that these smaller subtriangles are also similar to one another. All right, class, we have covered a lot of ground today, moving from the theoretical rules of similarity to how we actually apply them in the real world and in geometric proofs. Let's take a moment to recap the key takeaways from this lesson so you can consolidate what you've learned. Keep these points in mind, as they are the foundation for the more complex geometric proofs we will tackle in our next session. Before we move on, let's quickly look at some common pitfalls to avoid during your exams. Common mistakes. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even when you understand the concepts of similarity and medians, these small errors can lead to incorrect answers on your exams. First, let's talk about incorrect vertex correspondence. When we were proving the property of medians earlier, we established that triangle CMB is similar to triangle RNQ. A very common mistake is to write the vertices in the wrong order. Such as triangle CMB is similar to triangle RQN. This might seem minor. But in geometry, the order matters immensely because it tells us exactly which angles and sides are equal. Always double-check that your vertices correspond to the equal angles. Second, be careful not to confuse congruency with similarity. In our discussion on indirect measurement and shadows, the triangles we created are not the same size. One is the person and the other is the lamp post. Therefore, they are similar, meaning they have the same shape, but they are definitely not congruent, which would imply they are identical in both shape and size. Third, never ignore the vertical assumption. When you are solving these real-world shadow problems, you cannot simply assume a right angle exists. You must explicitly state that the objects, like the person or the pole, are perpendicular to the ground. This is the crucial step that allows us to use the angle-angle similarity criterion we discussed. Finally, watch out for calculation errors in ratios. Consistency is key here. If you set up your proportion as the height of the lamppost divided by the height of the person, then you must set the other side of your equation as the shadow of the lamppost divided by the shadow of the person. If you flip the ratio for one side, your entire calculation will be incorrect. Keep these points in mind, and you'll be well on your way to mastering these applications.